Okay, so just to recap, we've been talking the last couple of lectures about calculus, where we've been taking essentially this approach where we start with, to work out the gradient, we look at the change in the y-axis for any given change in the x-axis, and that's what these equations here talk about. So these are basically the same equation, except the one on the right here, the small change in the x-axis is just assigned it the variable h. So just to kind of keep things in mind that mathematicians and kind of scientists are really annoying in that they keep on changing the symbols for any one thing. Okay, so just to remind you that f of x is like what we call a function of x. So the easiest way to think about it is that's just y equals something. It's kind of like an equation that has x in it that is the function of x. And we went through last lecture, I think, where we took these equations with lots of different examples of the function. So x raised to the power of 2, 1 over x, where we work through and plug those functions into this equation here, and then we make h, or we make delta x really, really small, and then most of our equation went away. Okay? And that's, yeah, so this is just the approach here. So we've got, these equations at the top, they work out the gradient where you're looking at some definite integral. We're looking at some range of x changing and y changing. That gives us the gradient over some distance on the graph, and we're just making that distance smaller and smaller and smaller. Okay, so this where you've got big delta, that's where you've got some defined change in one variable, worked out the change in the other variable. That gives you the kind of average gradient over that distance. And then this terminology with the lowercase Greek deltas, that's where we've worked out at one point. So we've made this gap here, this delta x really, really, really small, or h really, really small, until parts of that equation magically disappear. Okay, hopefully, yeah, so that's differentiation. So that method that we used is kind of called differentiation from first principles, but we can make use of these kind of standard forms. Yeah, so hopefully you should remember this is kind of the most important. We worked out using that standard form, that first principle method. If we have x raised to the power of n, the first differential of that, or the gradient of that function, is this. So we bring the n down in front of the x and reduce the power by 1. Okay? So you can kind of think of that if we had y equals x to the power of n, the gradient would be y little tick, apostrophe, or nx to the power of n minus 1. Okay, and this is just another way of writing it. So this f dash of x, y dash, and dy dx all kind of mean the gradient of the equation y equals something, or f of x equals something. Okay? And then we went on to just to say that that's the case for kind of where you have x raised to the power of something, but there are also these other kind of standard forms, and we graphically went over some of the trigonometry functions here, but you can just imagine, so x, if y equals some constant, that doesn't have x in it, so it doesn't have a gradient. Okay, so the gradient is 0, so that's y equals a constant k, where k could be y equals say 2. There's a graph like that. Okay, the gradient of that is 0. Okay, y equals, if we had the graph of y equals x, that would look like that. Okay, that has a gradient of 1. Okay, and you could also think of that as y equals x to the power of 1, and we could use our y dash equals nx to the n minus 1 to show that that is actually, bring the 1 down, so that's 1 times x to the power of 0, which is equal to 1. Okay, so some of these can be derived from this standard form here, nx to the n minus 1. Others can't. Okay, and if you really want to know how to derive them from first principles, I mean, you can go and look in books, okay, but it'll take you forever. But you can we went through graphically why the gradient of sine x is cos x, and the gradient of cos x is minus sine x. Okay, so we went through some of those, and hopefully you will remember at least some of them. Okay, so I think most of you kind of got this one. You've got to multiply this out first, so you've got brackets with two things in it, so you multiply that, and that by that, which gives you 3x squared minus 3x. Okay, which is kind of... So when you're kind of faced with an equation like this, okay, and you're asked to differentiate it, it's always a good idea to see if you can kind of expand out brackets to give you something that's basically got multiple kind of functions of x plus or minus each other, okay, because then that makes it really easy to do the differentiation. And I think most of you got that that's 3 times 2 is 6, x to the power 1 minus 3. Okay, all good. And that is, I'm glad that was actually the answer. Okay, so I think most of you have got this next kind of slide down. Okay, so we've basically introduced these instead of just saying y as something or t as something, we've got this term called function of x or function of z or function of time or something, okay, which is just another way of saying y equals something, okay. Okay, and these are just some tedious examples. Okay, so we've just gone over this kind of first rule, whereas if you have two functions kind of plus or minus each other, you differentiate those separately and then add them together. Okay, and that's what we've just been doing. Okay, and this is also just reiterating that this is really tedious thing that dy by dx can also be written kind of f prime of x, or it can be of y prime if you're if that's the variable that you're substituting in for f of x. Okay, and we've been through these examples again. So if we were to differentiate this, y equals x squared plus x cubed. We just do those different parts separately, and if we have something in front of our x, so we have a constant times a function of x. Okay, we leave that constant there. Okay, if there was no x, if it was just a constant on its own, okay, if it was say x to the power of 6 plus 5, okay, we'd treat that as a separate function. Okay, and we know that if you've just got a constant, the differential or gradient of that function of just 5 is 0. Okay, so when you differentiate, constants disappear. Okay? Okay, and that's... Okay, and this is the second rule, which just kind of explains that if you've got this constant, okay, you leave that in front of the x. Okay, and I guess there's no point going over these, you did pretty well on the other ones. You kind of know that the answers to these are, the differential of this is y equals 6x, and y equals minus 18x. Oh no, it's not, it's minus, so yeah. We've got y equals 9 times x to the minus 2. I'll just make sure that you guys can do that. So what's the differential of what is y prime equal to in this case? Okay, so yeah, so 3 people have got it right there, and 1 person's got it wrong. Because this is raised to the power of -2. Okay, when you do n minus 1, if n equals -2 is -3. Okay, so in this case, this equation would be -18. So -2 times 9, -18 times x to the power of -3, which is the same as saying -18 over x cubed. Okay? And we will get rid of that. But I just want to just go through this example. Okay, so particle moves in such a way that so we've got an equation that describes the position of something. Okay, its horizontal position or whatever. Okay, with respect to time. Okay, so it's 27 time plus minus 2 times squared. Okay, so we could use that if we were asked a question about the velocity. We could differentiate that equation. Okay, to work out the velocity. So the velocity, if x is equal to 27 times minus 2 times squared, okay, velocity is the rate of change of position. Okay, so if this is kind of how many meters you are away from the start, okay, the velocity will be the change of distance with time. So you could write that as the change in distance, change in time. Okay, and that's basically, if you can imagine substituting into this equation, that would be y, this time this would be x. Okay, you can see how this equation, just because we're not using x and y, you can kind of like substitute those guys back in there. So this would become 27 minus 4t. Happy campus with that? Okay, and then if we wanted to know its velocity, okay, we could plug 6.75 into that, which I'm not going to do, and that would give us that instantaneous velocity. If we wanted to know its acceleration, okay, so the acceleration is the rate of change of the velocity. Okay, so we could differentiate this again. Okay, so we could kind of write dx dt kind of dt. Okay, or we could say, well, if this is actually equal to x prime, this is actually equal to x double prime. No, you're not that impressed, are you? Okay, so if we differentiate the equation for the velocity, okay, 27 is just a constant. Okay, so if you differentiate a constant, okay, this part of the equation becomes 0. We've got minus 4t, so our imagine that's t to the power of 1, bring that down to the front, so that's just minus 4. Minus 4 times 1 is minus 4, and that's t to the 0, which kind of goes away. So our acceleration is minus 4. Okay, so that's kind of a deceleration. Okay, so we can do that, and that's pretty good. That means at any point in time we know how fast the particle is going. We know how it's accelerating, or in this case decelerating. Okay, so we can do all those kind of fancy things. And we could do all these things. How long does it take to do all these kind of jobbies, right? Which is great. But we can start to be more intelligent with these differential functions. Kind of more intelligent. Okay, so in this case, just flip through these. Yeah, so rather than just starting out with something that we know an equation that gives us the position through time, and then we differentiate that to get the velocity or acceleration again, something like that. We could start out with kind of a scientific idea, and from that we can then construct our own differential equation. Okay, and this is kind of the hardest part of the maths course. Okay, if we start out with something like this, Okay, so the rate at which the height of a plant increases is proportional to the natural logarithm of the difference between its present height and its final height. Okay, so this is a scientific theory. Okay, so this means that if you've got some tree, okay, that's a tree, right? Just go with me, okay? So if you've got a little baby tree, if this is a really old tree, so really old trees are all kind of the same height. So they grow to some like maximum height, and then they go, oh, that's the height I'm going to grow. And they fall over and die. Okay, so if you've got like a little baby tree, okay, the rate at which that grows, okay, is proportional to, this is the final height, h, okay, and this is the present height. Can't remember what the symbol is, but let's say HP, present height, HF. Okay, and if this distance is very, very big, if the difference between them is very big, it grows quite quickly. Okay, and as it gets progressively taller, it starts to reduce in its height. It reduces in its rate, it grows more slowly as it gets taller. Okay, so we need to think about what kind of equation we're going to draw to start with here. So we know that the rate of height change, okay, so we can write that as maybe dh dt, okay, yeah, is proportional to, we just put proportional to at the moment, is proportional to the natural logarithm, so that's just ln, okay, times the difference between its present height and its final height. Okay, so it'll be hf minus hp. Okay? Now, I've put proportional in there, okay, but if you just imagine, just forget that this is a logarithm over here. If you had a graph of y and x, say, okay, and we just had a straight line on that, okay, so any change in y is you get a change in x, okay, for any line, yeah, any straight line. The only thing is different in these, so you can describe all of these graphs by an equation that y is proportional to x, okay. You could also describe those as y equals some constant, could be any number, okay, times x, okay. So if you have an equation that you come up with that's, say, proportional to something, that's the same as it's equal to something, but you don't know what the constant is, okay. So we just don't know the slope, okay. If we wanted to know the slope, we'd have to have some actual measurements that allow us to figure out some points on the line, and we can work out the gradient. Okay? So in this case, we can say dh dt is equal to k natural log of h, the difference in the heights. Okay? Okay, we can have another kind of equation, okay, and this is kind of real science. This is physics here, okay. So the law of cooling, okay, states that the rate of change of temperature, okay, is proportional to the difference between its surroundings and the ambient temperature. And that's kind of obvious. If something is really, really hot and you put it in a cool room, it will cool down quickly. Yeah? Whereas if it's not so hot and you put it in a kind of not so cold room, it won't cool down as quickly. Okay? So you could do the same kind of thing for that. You could start out with the change in temperature for time, yeah, is equal to some constant, or you could say is proportional to, and you put constant to, it's proportional to the difference between its own surroundings and the ambient temperature. In this case, it would be proportional to the temperature of the object minus the temperature of the environment. I'm going to put TE. Okay? So if this number is much bigger than this number, okay, so if our object is very, very hot, okay, the rate of change is going to be very, very big. Okay, it's going to cool down quickly. Okay, but because it's cooling down, temperature is becoming more and more less positive. Yeah, if something cools down, it starts off hot, big number, small. So actually, we know that our constant is negative. It must be negative. Otherwise, things would heat up if you left them in a cold room. Okay, and those are... Oh, sweet, I almost got those right. Look at that. Okay, so you can imagine now we've now created a differential equation. We've created an equation that describes the gradient of something. Okay, now what we can do, okay, is if we do the opposite of differentiation, we could go back, okay, to create an equation that describes the temperature at any time or the height of the tree at any time. Okay? Okay, so if we had, these are these two equations, so we have two differential equations, okay, but rather than starting up here with something that describes how something, the amount of it changes through time, okay, we start out kind of in the middle. We start out with something that's already been differentiated, okay? So if we in fact go back, okay, if we do the reverse of differentiation, okay, we could go back and create an equation that describes how these things change through time, which is a really useful part of science, okay? Being able to come up with a differential equation that describes your scientific theory, and quite a lot of our scientific theories do involve the rates of change of stuff, okay? We actually start in the middle and then we work back to our basic equation, which turns out to be much more complex than these, that allows us to describe the system, okay? Now, we won't do that today, we might do some of that tomorrow, okay? But this is just a little bit of a taster of what's going to hit you in EMP 2, okay? But this is kind of that first part of what we did, where we took an idea, just an idea, okay, and then turned it into a differential equation, okay? That is part of this course, if you have looked at the exams. Anybody looked at the exam for last year? Blank faces coming back. I posted it on Learn, so if you look on Learn, at the bottom of the first page, there's a thing that says exam help, and in there is last year's exam. Okay? So have a look at that. I think Massimo also emailed you some stuff. Did he email you stuff? No, maybe not. So in the tutorial later on this week, your tutors will almost certainly go over past exams with you. So have a look at the one on Learn, okay, just to get you in the zone and give you something to talk about with your demonstrators in the tutors in the tutorial. Okay, so we're going to talk a little bit now, as we're coming towards the end of today, about these higher derivatives. So what you actually get when you differentiate something and then differentiate again and then again, okay? Why that's useful? Why do we it's not just giving us information about the velocity of something and then the acceleration of something by just doing multiple differentiations of the same equation. Okay, so we focused mostly on just differentiating something once. Okay, so actually, that's how you write the second derivative. So what did I write something? I did something crazy earlier. Okay. So if you differentiate, if you've got y equals some function of x, right? Okay. If I wanted to do dy dx, that's the same as f dash of x. Okay. And if I wanted to differentiate it again, okay, you'd use this terminology here. So it would be d squared of y dx squared. I have no idea why you use that terminology, but if you're differentiating something twice, you've got these squared above it, and that would be the same as writing f double prime of x or y double prime. Okay, it's just terminology. Okay, and why would we want to do that? And we kind of went through this the other day with the throwing stuff as high as you can without touching the ceiling thing. right, which is the drinking game you've done. No, you go around in a circle and throw something as high as you can without touching the ceiling. The person who gets as close without touching the ceiling wins, and then if you touch the ceiling, then anyway, it's a field trip game. So we can use. It's just like bad advice. Anyway, never mind. We can use this kind of differentiating things multiple times to work out kind of interesting points on graphs. Okay, and that sounds like really super nerdy. But it's not just interesting points of graphs, it's things like when like a ball reaches its maximum height, or maybe when the tide kind of reaches its kind of maximum extent, starts coming back in. Okay? These things where you're looking at rates of change of things, when is something changing its fastest, and when is it changing its least fast, when is it zero. Okay, so we can use calculus to work out these kind of like points. Okay, so these are termed stationary points. Okay, where gradients are zero. Again, that's just terminology that mathematicians like to use to feel clever. And the really cool thing is that you can find these if we work out the first derivative, okay, and we set that to be zero, and then we solve that equation, and that allows us to work out some points on the line. And the cool thing is, it's really not cool, but is that, say in this example here that we've got up there, if this was our function, okay, and we found by differentiating this is okay, if we differentiated that, we could find out where this is y and x. If we wanted to look at y star, we could find out points that were zero, that maybe, and we could see, well, we've got a positive gradient here, and it kind of, then it becomes a negative gradient, a positive gradient again, and we get back down to negative gradient here. So we could do some shit like that, right? And this gives us this is the gradient of this graph, okay? Now, we could run out of colours. And this would tell us, if we said when that gradient was equal to zero, that would give us these points on the graphs here, which would tell us these points here, right? But we can be a little bit more intelligent about that, and we can tell the difference between a point that's like this, like a frowny face, and a point that's like this, it's a happy face, by differentiating this equation again. Okay? And we can do that, and if we do that, we can see over this portion of the graph here, we've got a positive, it's positive gradient until we get to here, and then it's kind of like a negative gradient. Oh no, that's all the way around. Tool. This bit of the graph has got a negative gradient. Happy campers, yeah, so if we differentiate that, we get something that looks like that. Positive gradient, and then it goes down to 0. And then here we've got a negative gradient again, and a positive gradient. Okay? And at this point here, we can see we've got a negative gradient. Okay? So that means we've got a frowny face because the gradient is getting less and less and less positive each time. Whereas in this point here, we've got the gradient is increasing as you go through the stationary point. Okay? So by doing the next derivative, that tells you what kind of stationary point it is. Okay? So we can tell whether it's kind of a frowny, smiley face or a happy face. Okay? If it's at the 0 here, we can't tell us anything. Okay, so I'm just going to go through these examples of, say we had an equation that was 2x cubed minus 6x squared minus 18x. Okay? So, I think, okay, and there's this other example at the bottom which we might get to. I probably can't do it myself. So just for the top guy there, okay, I want you to work out where the stationary points are. Okay, so to do that you have to differentiate it and then set the gradient to 0 and then solve that equation for x. Okay, so this is the kind of thing that is exam. I haven't actually seen the exam by the way. So one of the reasons I didn't get full marks on the exam last year was that I stuffed up an equation like this and got it wrong. So I don't know if I've. Oh, yeah. So you can see this is the equation at the top here, and this is kind of uppy, downy, uppy is kind of a typical form of an equation like this that's got an x cubed in it. So this is a cubic equation. Okay, x cubed minus x squared something minus x something gives you kind of an uppy, downy, uppy. Okay, and then so remember to differentiate that. It's this time we've got three functions of x. So we've basically got a constant 2 times x cubed. So that's our first function. And we've got minus 6, which is a constant, times x squared. And then we've got minus 18 times x to the power of 1. Okay, so there are three separate parts to that. Okay, and we can differentiate those. So the first part, 2 times 3 is 6. And then you reduce the power by 1, that gives you 6x squared. Minus 6 times 2 is minus 12, and then you reduce the power by 1, so that becomes x to the power of 1, which is just x. And then we have minus 18 times x to the power of 1 times 1. Okay, so that's just minus 18, and then x to the power of 0 is 1, so that kind of just magically disappears. Okay, so that gives us this graph here. Okay, so all we have to do is then write an equation where we make this y equals to 0, or y prime, so this should be y prime over x here, make that equal to 0, okay? And that's a quadratic equation, right, which you should be able to solve, okay? So there are three methods to solve the quadratic equation, okay? One is the factorization, you just put the two brackets in and you kind of figure out what numbers should be in there, okay? You could use the perfect square method, or you could use the, the one b minus b squared something square root of 4a minus 8. Those aren't the actual equations, I can't remember it, which is why I stuffed up the exam. Okay, so learn the shit out of it. Or actually just write it down in your notes, right, because you're allowed to take your notes in. Another reason I failed the exam. I didn't fail, I just didn't get. I got fewer marks than students, which was embarrassing. So hopefully you can solve this equation to work out these stationary points here. Okay. Solve it. Okay, so I'm going to try and solve it by factorising shit out here. Okay, so I know I'm going to have one bracket times another bracket. Both of those brackets are going to have an x in them. Okay, and it's going to be plus or minus a number. And I can see here, because this one here, okay, that's a minus. So when I times this number that's going to be here by that number there, okay, it's got to end up being a minus. Okay, and the only way you can do that is if they're different. Okay, so if they were both minus or they were both plus, that would end up being positive. So I know that one of these is minus and the other one is plus. I might have them the wrong way around, but okay. And I know that because this is a minus here, I've got to basically make up something that's times x that's going to give me a big negative number. Okay. The other thing I've got to think about is I've got to make 6x squared, so I need something to go in front of these things. So it could be 6 and 1. Okay, could be, but I'm not going to do that because I don't think it's 6 and 1. I'm going to go for, I think it's 3 and 2. Okay, so I now need a number that's going to times itself times by 3, and another number that's going to times by 2 that's going to end up adding and taking away to be 12. Okay, so I'm thinking that I want to get something big and negative, okay, and then something to add on to that to make it less negative, okay, because this is a negative 12. And I've got a 3 and a 2. It's going to be 3 times something, and then 2 times something, and one of them's going to be big, one of them's going to be kind of like a bit smaller. So I'm going to go for, I'm going to try and get something that's 18, and then take something away from it to make it 12. So that's looking for an 18 and a 6, right? And those, I'm thinking of those because 18 is 3 times something, or 9 times, or 2 times something, okay? And I can also make 6 out of 3 and 2. So in my mind, those things are working, okay? So if I try 3 times what was I looking for? 3 times 6. Yes, 3 times 6. If I make this 6, so 3x times 6, that's 18. Okay? And then if I make that 3, okay, 3 times 2 is 6. So that kind of helps me out. Except that now, when I multiply this out, that gives me 6x squared, 3x times 2x. Great. Then I've got 3x times 6, that's 18x, okay, minus 6x. Okay, so I've got the signs wrong. So I can make that plus and that minus. Okay? So I could then say that, well, one of those, if this is 0, one of those has to be 0. Okay? So I could say 3x plus 3 is 0. So that you can rearrange that to get x equals minus 1. Yeah, so if 0 equals 3 plus 3, that just becomes minus 3 equals 3x, and then you just, that becomes 1. Yeah, so I've got minus 1, and this one will turn out to be 3. And if you look at the graph, that's kind of what we expect. There's 3, there's minus 1. Okay, so you could have solved this using that generic equation for solving quadratics, and that would have probably been faster. Okay, so don't feel like you have to use this method, or you have to use the perfect square method. Okay, but if you can spot it straight away, then fill your boots. Okay. Okay, but it's not just, okay, the smiley face. If we differentiate it again, okay, so now we've got this y prime equals 6x squared plus 12x minus 18. If we differentiate that again, so in this case we want y double prime, or is it d squared y over dx squared, okay? If we differentiate that again, okay, we can then look at these parts again separately. So we differentiate that separately, and that separately. 6x squared becomes 12x. Happy campers. Minus 12x just becomes minus 12. Okay, or minus 12 times x to the power of 0, which is 1. And then minus 18, that just disappears. Magically goes away. Okay, so this gives us this equation, 12x minus 12. Okay, and that's this graph here. Okay, So we can then say at each of our stationary points, okay, so at each of our stationary points, at -1, okay, this equation gives us a negative number. Okay? If we make -1, well, minus, is that right? Yeah, so should be 0. How do I fuck that up? It looks perfectly fine, right? At -1 here, we've got a negative value for our y double prime. Okay, and if we look at the equation up there, at -1, we're decreasing the gradient. Yeah? So that means that it's a Brownian, so it's a maxima. Whereas at 3, we've got positive, that's on this axis. Okay, so that tells us that we've got a minima, so we're increasing our gradient through time, or through as we increase x. Okay? So, I just don't know why that's wrong. 12 times -1 is minus... 12 times -1, idiot, is -12. -12 is -24, which is there. Okay, so it doesn't give you 0 at -1. Okay, that's correct. I'm not a retard. Well, not sure one anyway. Okay, so that is us for today. I think. Oh, yeah, there we go. So it's +1. Okay, so you can see if you can try and solve this one if you want to. You'll need to remember the stuff about vectors. That's us for today.